Hello there everyone, welcome back. Our next video here is really the start of our look at quantum physics, which despite what you've heard about quantum physics, I can assure you it is in fact much weirder than what you're expecting. So again, like with every topic this unit, we're just going to look at kind of an overview, and you can definitely dive very deep into this stuff, but we're just going to try and get you an idea of what it means to talk about things that are quantum. And the first thing to think about is right in that word quantum. So quantum itself really just refers to a small amount of something, a small unit of something. And that's the idea of quantum, is that it's going to really apply to masses and energies on really small scales. That's the first thing to think about. So I want to draw your attention here to this graph that you see here. This is something illustrating kind of a classical problem in physics. And I mean that in the sense that classical physics, if you look at sort of, the early 1900s, had really thought it had solved a lot of the problems of physics. And they kind of thought they'd had everything all wrapped up in a nice, neat bow. But there were just a few last little problems they couldn't quite figure out. One example of those is this idea of the black body problem, or the ultraviolet catastrophe. So essentially what a black body is it's just some object that will absorb basically every wavelength of light. An example of that would be like our sun. Our sun will absorb basically every color of light, and we know that because the flip side to that is when you energize a black body, it emits basically every color of light. When you look at our sun, and if you split the white light from it up, it's going to give you every color of the rainbow. And in addition, it's going to give you wavelengths of light that we can't even see. So the sun is a black body. You can think of other things, like maybe not a perfect black body, but like a chunk of steel, right? If you take a piece of metal, like a chunk of steel, and you heat it up really hot, it's going to glow. And what you might notice is that it glows different colors. It glows red, and then white hot, and then eventually maybe even blue hot. And that's what's happening here. So when we observe objects that are highly energized, that are very warm, for example, at a temperature, in this case of 5,700 Kelvin, they glow and they emit radiation. And the cooler they are, the more they tend to glow in the red kind of range, and then maybe a little warmer is kind of orangey or yellow, and then eventually they glow essentially white hot. And then as we get hotter than that, they start to glow blue hot. Now, the reason for this is just because of the distribution of the wavelengths that they're emitting. Okay, so at a really low temperature, when I'm kind of glowing red hot like a light bulb, you can see the peak of this curve is really happening in the red range of the spectrum. And so I'm emitting all wavelengths of light, but I'm emitting so much more red that that's really the color we're going to see. As this gets warmer, the peak tends to happen in yellow or orange, and so it takes on a yellowy orangey hue. Now, eventually it starts to glow white hot. And you might ask, well, why not green? Because the peak is right there in the green. And the short answer is, well, yes, the peak might be in the green, but there's so much of the other wavelengths around it that overall this is going to appear white. And then as we continue on, eventually it starts to glow blue hot because this peak shifts way over and we're emitting enough blue that overall it looks a bit bluish. But that's not really the problem physicists were trying to solve. So we sort of understood this idea. And I guess it makes sense. If you have matter, and that matter is energized, then it's going to emit energy. And why not emit light, right? That's a form of energy it could emit, just like heat. So that's all fine. But the problem comes when we look at what classical physics projects versus what actually happens. Now, this graph here, don't worry too much about what it's showing on the various axes, but just understand this y-axis here is spectral radiance. You can think of that as kind of how much energy is being emitted in a place. And then along the x-axis here, you see wavelength. So notice that as I travel, as I go to the left, my wavelength is getting smaller and smaller, which means as I go this way, my energy is actually increasing. And so what classical physics kind of predicts is that an energetic object is going to emit all different wavelengths of light. And since as the wavelength gets smaller, the energy gets higher, I'm eventually going to trend towards an infinite amount of energy. That's why this is called the ultraviolet catastrophe, because as you go towards the ultraviolet, you just start emitting more and more energy. And we don't see that. You see, these curves kind of follow each other, but as you get here, for example, following this blue curve, you can see that it drops off dramatically back down to zero. So that was a problem. Now, what Max Planck did to kind of help solve this problem is he said, okay, let's imagine that the black body is made up of what he called thermal oscillators. So that these atoms that make this up, they're kind of oscillating back and forth, and they oscillate at specific frequencies. And then these frequencies, these oscillators have discrete quantities of energy. Now, what we mean by discrete in this case, discrete means like some specific amount. And so he said, listen, even though the smaller wavelength light is very energetic, it's just not very likely to happen. So he brought this idea of probability into it as well and said, okay, it makes sense that the amount of energy drops off at a higher energy because there's not much of that light being emitted by the body. Most of the light is being emitted at the lower energy levels. So he came up with the quantum hypothesis, which says that E equals H times F. Now, some of these terms are going to be familiar to you. In fact, you can already probably guess that E is energy. And we're talking about energy of light, and more on that in a second. F, of course, is our frequency. And so we can see that the frequency of the light is directly related to its energy, which again is probably not a big surprise. We've talked about that a bit so far. And then H is simply a constant. In this case, it's called Planck's constant. Isn't that nice for him? Now, Planck's constant is very, very, very small. And that's kind of what quantum's all about, very small things. So 6.63 times 10 to the negative 34, and it is measured in joule seconds, okay? So if you want to know the energy of a particular packet of light, you can just multiply the frequency times the Planck's constant. Now, Einstein then built on this idea and said, okay, so if we've got these thermal oscillators that are producing light at really specific frequencies, maybe we can think of light as being like these discrete particles. And again, what we mean by that is just like these little units, these little packets, these little bundles of energy. And he called these things photons. Now, this is the ongoing debate. You see, as we talked about before, scientists had been debating as to whether light was like a particle or a wave. When you look at, for example, reflection, that's sort of exhibiting particle-like properties, like a marble bouncing off a wall. Whereas when you look at refraction or diffraction, light is exhibiting wave-like properties. After Young conducted his experiment, a lot of scientists just agreed, okay, that's it. Finally, we know light is now a wave. And then quantum physics comes along and turns it all on its head and says, well, yeah, but also sometimes it's a particle. So light is just very weird. And sometimes it behaves like a wave, and sometimes it behaves like a particle. And we're going to talk about that a bit more as we move on. So these particles of light, these photons, can only be absorbed or emitted in whole units. So they are these, again, discrete packages. And each light particle or photon has an energy and frequency, an energy that corresponds to its frequency in the Planck's constant. So let's think of this example. Imagine you turn on a light bulb, and this light bulb, it's a 60-watt bulb. And so it's emitting photons all over the place. Well, how many photons are coming out of this light bulb every second? Now, if we assume that the light bulb is about 10% efficient at converting the energy into light, and then the average wavelength is about 550 Newton meters, how many photons per second is that? Okay, well, the first thing to think about is, so 60 watts, multiply that by 10%. That means we're going to pump out about 6 joules per second of light energy, of electromagnetic photons, all right? And so we know from our Planck's hypothesis that the energy of the photons is equal to H times F. Now recall that the frequency is related to the wavelength from this formula, V equals lambda F. So essentially, F is the speed divided by lambda. And if I sub that back into my Planck's formula, then I get this right here, E equals H times V over lambda. And V in this case is sometimes just written as C because we're talking about light, and so it's the speed of light, but we know that. So solving for the energy of one particular photon, I've got 6.63 times 10 to the negative 34 times 3 times 10 to the 8, divide that all by the wavelength, which is, we're assuming 550 nanometers. So that's 550 times 10 to the negative 9. Don't forget that nano is negative 9. So crunch all these numbers together, and we're going to get a fairly small number. Each photon has an energy of about 3.62 times 10 to the negative 19 joules. Now that's how much energy, that's like the joules per photon. So if I'm pumping out 6 joules of energy, how many photons must be going along for the ride? Okay, well, I guess the number of photons let's do that over here. Number of photons would really just be the 6 joules per second divided by the energy of one photon, 3.62 times 10 to the negative 19 joules per photon. And you can check my units there, make sure I got that right. But again, put this all together, and we're talking about 1.7 times 10 to the 19 photons every second being emitted from this light bulb. So you can see that scientists would have been forgiven for not noticing photons because they're very, very small. And when you shine a light, there is a whole stream of many, many of these photons that, again, sometimes act like waves or sometimes act like their own little discrete particles. Now, the second thing that scientists had a hard time explaining using classical physics that really pointed towards something else that was going on was this idea of atomic spectral lines. Now, the way this works is if you were to take an element, in this case, let's say hydrogen, okay? And you were to energize that hydrogen. Maybe you pass a current through it or something like that to just give those hydrogen atoms a bunch of energy. Well, they're going to want to get rid of that energy. And one way they can do that is to give off light, just like we saw with the black bodies. Now, the thing is, though, if you have a sample of pure hydrogen, then when it emits light, it's only going to give light that falls on the hydrogen emission spectrum. It's not going to give you a full rainbow. It's going to give you this one specific spike of red light, and then this one specific spike of kind of bluey, greeny light, and then this blue, and then these two violet lights there. Now, those specific spikes correspond to an exact wavelength of light, which means it corresponds to an exact frequency of light, which means it corresponds to an exact energy of light. So for some reason, you can give hydrogen a bunch of energy, and when it emits light, it only emits that light in very exact chunks, almost as though that hydrogen atom is emitting very specific amounts of energy. And that's what's happening. These represent specific photons that hydrogen is able to produce. And each element is only able to produce specific photons. Now we'll talk about why that is in a second, but maybe just jump back to this idea of a black body, back to blackbody radiation. The fact that our sun gives off a whole rainbow of the entire rainbow, if you will, is because, well, the sun is made of virtually all the elements that we have access to in our solar system. And all those elements together, emitting all those different spikes of light, kind of add up to a complete rainbow. If you were to look close enough, though, you'd actually notice little gaps that are missing in that rainbow. Okay, so back to hydrogen. So this bottom here, we see black with the colored spikes. That's the emission spectrum. So let's say we do another experiment. Let's say instead of taking our hydrogen and energizing it and then seeing what comes out, let's take our hydrogen and shine pure white light on it. Now, if we do that, if we've got our hydrogen sample, we shine pure white light on it, and then we collect the light that comes out the other side, and we take a look at it, then we notice this. We shine pure white light, which is a full rainbow, and then what makes it through has these little gaps in it. And you'll notice that those gaps perfectly correspond with the absorption spectrum. So all of these little gaps that are missing correspond. Now again, why is that there? Well, when you shine white light on hydrogen, it's only able to absorb very specific frequencies of light, very specific energies of light. So why is this? Why can a particular atom only absorb very specific photons and then emit those exact same photons? So each element will only absorb light at a very specific frequency. And remember that that frequency corresponds to a specific energy level. Okay? Now, Bohr got around this by kind of saying, okay, well, maybe what's happening, you can think of the Bohr diagram. We've got these electrons that are orbiting around our nucleus. Maybe the orbits of those electrons, since they're going around in a circle, they have angular momentum. Maybe that angular momentum is discrete and can only have very specific values. So, like, for example, the electrons, he thinks of them as being in these energy levels. They can be in the first or the second or the third energy levels. And that's what he thought of it as. The Bohr model refers to these things as our energy levels. So we can only have electrons existing at really specific orbitals or energy levels. And he called the lowest possible energy level the ground state. Okay, so electrons want to live in the ground state. In this example here, in this diagram, you can see there's my electron, and it's living in the ground state. We call it 1, all right? Now, we're going to use hydrogen as our example here because, frankly, hydrogen is the simplest. And when we start talking about larger atoms, even just helium, things get pretty complicated pretty quick. But the basic idea is still the same regardless of how complicated the electron structure is for the atom, okay? Now, you could get that electron to go up to a higher energy level, right? You could get that electron to jump from this energy level that it's at right now, the ground state, and you could convince it to jump up to a higher energy level right there. And now it's going to exist at a higher energy level known as an excited state. Now, how could you do that? Okay, well, we'll talk about how we get that there. Before we do, though, if you wanted to, you could get it to jump up to a higher energy level, or you could completely rip it free. You could give that electron so much energy that it completely comes free of the hydrogen atom. And in that case, that we would be referring to the ionization process. So to completely rip free an electron, that is going to take something called the ionization energy. Okay, so what's happening there? Well, the first thing to recognize is if you want that electron to jump, let's say not completely free, but just go from the first energy level up to the third energy level. Notice that the difference between the first and the third energy level is a very specific jump. It's a very specific amount of energy. And what Bohr said was those energy levels are quantized, which means you can only exist at the first, the second, or the third, and so on energy levels. There's no such thing as being at the 1.5 energy level, which is a strange idea because classical physics would say, well, yeah, you could be halfway in between, you could be partway up the hill, and so on. And quantum says, no. Life, the universe, is not like a continuous line. If you zoom in close enough, it's actually a series of little tiny steps. And you can be on the first step or the second step, but you can't be in between. When this electron goes from the first to the third orbital, it ceases to exist at the first energy level and it starts to exist at the third energy level. There is no in-between time. There's no lag. So how does it do that? Well, in order to jump from the first to the third energy level, one thing it could do is it could absorb a very specific photon. If I hit that with just the right energy photon, then that's just the right energy level that corresponds to a jump from the first to the third energy level. And so when an electron transitions, it's all about getting the right amount of energy to do that transition. Okay? Now imagine that electron is now orbiting around in that excited state. So now I'll just draw it over here so I've got some space. So I've got my excited electron up in that third energy level. It doesn't want to be in the excited state. It wants to come back to the ground state. But in order to do so, it would have to make this jump, it's going to have to get rid of some energy. So it can jump back down to the ground state, and then it'll be much happier there. But in order to do that, it has to emit energy. And the energy that it would emit would be, again, a photon. And that photon would be the exact same energy as the photon that was required to make it jump up, which explains why our emission and our absorption spectrum line up perfectly. You're going to absorb a specific wavelength of light, and then you're going to emit a specific wavelength of light. And that's why these two, the gap and the spike, are in the same place. Now, it's worth pointing out that if I have another electron, let's say, and this hydrogen is getting very crowded, but just bear with me. If I have an electron here in the excited state, I could jump down to the first energy level. That's one possibility. But instead, I could take the long way, and I could jump down to the second energy level and then down to the first energy level and kind of do that same journey in two jumps. And that is, of course, totally allowed. Now, each time you drop an energy level, you're going to emit a photon. But of course, you're not going to emit the same photon as you did when you jumped from 3 to 1. You're going to emit two different photons. So for example, perhaps in this first jump, I emit one photon. And then in the second jump, I'm going to emit a second photon. And what you would notice is the energy of those two lower energy photons would add up to the exact same energy as that one higher energy photon. The total energy has to be the same. Okay, so when we've got an electron transitioning from an excited state down to a ground state, it's going to emit a photon. All right, and the energy of this photon is equal to the difference in energy between the levels that it transitioned to and from. So therefore, only a photon of a particular frequency or energy can be emitted in that particular transition. And then the same is true for absorption. The absorption can only happen at a very specific frequency. The same frequency that it's going to emit is the frequency that it's going to absorb at. Okay, so this helps explain our second problem, which is that why is light emitted at very specific frequencies? So we'll do an example here. Now, in this example, we've got, you can use a spectrometer. And if you don't have a spectrometer, well, I'll help you out in a second. But you can use a spectrometer to observe the light coming off of energized hydrogen. And if you were to look at it, again, you would see you've got like this red line here, and then kind of the bluey green line, and this other blue line over here, and so on. Now, that red line happens at a very specific frequency. So the wavelength of the red line happens at a wavelength of 657 nanometers. And then the blue spike that we see, that blue spike is going to happen at exactly 486 nanometers. So what we've got here is we've got a diagram that's going to help us kind of understand how that happens. So what we're trying to find is what energy transition is going to be responsible for the red light and is going to be responsible for the blue light. All right. So, well, let's take a look. What do we have? So this is showing us our different energy levels. And you can see here on the side, this is our energy levels. It goes from the first energy level up to the infinitieth energy level, if that's a word. And all that's saying is, okay, the first energy level here, this is my ground state. Okay. And this is where the electron wants to be. And then all the way up, so you can see we go from 1 to 2 to 3 to 4, 5, and so on. And there are many more here, 6, 7, 8, 9. I just haven't drawn them in. But it goes all the way up to infinity. And at this point, you have just ionized. Okay, so this is my ionization energy that I was talking about before. So if you want to completely rip that electron free, you go all the way up to there. Now, it counts from 0 down. Right? So my ground state is some negative number, and as I jump up, I climb up to a smaller and smaller negative number, all the way up to 0, which is when I'm completely ionized. Now, this other side, you can see that so we can see that this scale is showing us energy, but the units that they're giving us are something called EVs. Now, EV is an electron volt. So 1 electron volt is the energy of 1 electron sitting at 1 volt. It's a very creative unit. And so you might remember that the potential energy for an electron would be the voltage times the charge. And so 1 electron volt would equal a 1 volt times the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs. So that's going to correspond to 1.6 times 10 to the negative 19 joules, and that is 1 electron volt. So that's like a little conversion factor that we might have to use. We tend to use electron volts when talking about these quantum things because the amount of energy that we're going to have, that electron's going to have, is going to be very small. And so instead of using joules, we might use electron volts. Okay, so let's think about this. Now, remember that any transition is possible. Any transition where I start at an excited state and drop down to a lower state is going to produce a photon. And so the question is, how can I make the red and the blue photons? Which jump is going to kind of correspond to that? Well, I don't know where to start, so I'll just start at the simplest one I can think of, which is, okay, let's just imagine what would happen if I started here at the n equal to 2 state and I dropped down to the ground state. So what wavelength of photon would that produce? How much energy is in that photon? And then I can go from there. So the first thing to think about is my change in energy. So the energy difference from 1 to 2 would just be the final minus the initial, right? Which again is going to be in electron volts. So that's going to be negative 13.59 minus negative 3.4. And so that is negative 10.19 electron volts. Now, you can leave it in electron volts and work with that, but I just like to work in joules, so I'm gonna do that. Now, the other thing to notice is that it's negative. So that's just because the electron lost that energy. So if the electron lost that energy, then the photon would correspond to a positive amount of energy. And so 10.19 electron volts times 1.6 times 10 to the negative 19 joules for every 1 electron volt is going to give me a total of 1.63 times 10 to the negative 18 joules. Okay, so the transition from 2 to 1 is going to produce a photon of 1.63 times 10 to the negative 18 joules. Okay, but I need that in wavelength before I can compare it to my results. So remember, we have our energy is equal to HF, and then we learned that energy equals H times V over lambda, which means that lambda is just going to equal H times V over E. Subbing in all of our values, 6.33 times 10 to the negative 34 times 3 times 10 to the 8, all divided by 1.63 times 10 to the negative 18 joules, comes out to a value of 1.22 times 10 to the negative 7 meters, which is 122 nanometers. So there we go, 122 nanometers, except that's not really the answer we were looking for. The drop from 2 to 1 produces a photon with a wavelength of 122 nanometers. Now, the blue light that I made was the highest energy that I'm interested in, and this is much smaller wavelength, which means it's a much higher energy. This 122 nanometers is actually going to be off in probably the UV end of the spectrum, so I wouldn't even be able to see that. Now, that was the simplest transition I could think of that ended up at the ground state. Or I should say, it was the lowest energy transition. If I went from the third energy level all the way to the ground state, well, that would be even more energy, which means my wavelength would be even smaller. So there's no way that the transition that I'm interested in is one that ends up on the ground state. So I can rule out all other transitions that end up at the ground state. So just by process of elimination, I can say, okay, well, what if I start at the n equal to 3 level and I drop down here to n equal to 2? Now, I've run out of space and we've done the calculation once, but you could imagine just rerunning this whole calculation all over again. And what you would find is when you go from 3 down to 2, this corresponds to a wavelength of 657 nanometers. Okay, that's that small enough energy to produce that photon of red light. So what about the blue light? And lo and behold, if you check the transition from 4 all the way down to 2, you're going to see that corresponds to a wavelength of about 486 nanometers, which is our blue light. All right, that is it for part 1 of our look at quantum physics.